Let's take a look at the combination sum problem. In this problem, we are given a list of positive unique numbers and a target number. Our goal is to find the number of ways we can use the numbers in the list to add up to our target number. An important detail is that the same combination of numbers, but in different order, are counted twice. So for example, if our target is 3 and we have the numbers 1 and 2, our answer is 3 because we have 1 plus 1 plus 1, 1 plus 2, and 2 plus 1. So while this problem is known as the combination sum, I think the better term is permutation here because we do make distinctions between the different order of numbers. So just as a note, I'm going to use combination for the rest of this video just to keep things consistent, but we are really talking about permutations. So let's take a look at another example where our target is 4 and we have the numbers 1, 2, and 4. We would return 6 as the answer because there are 6 possible ways we can add these numbers to sum to 4. So now that we have discussed a couple of examples of the problem, I encourage you to pause the video and try this problem for yourself if you have not already. Assuming you have given it a shot, let's move on to the first solution. The first solution is to use recursion. The overall idea of this solution is that we're going to start with a target, and we are going to use a for loop to subtract off the first number in the num list from our target. If the subtracted number is still above 0, we explore a new recursive branch with the subtracted number serving as the new target. Our base case is going to be if the target is 0, because that means we have perfectly subtracted off from the target to reach 0. Our other base case would be if the number falls below 0, because it means we have overshot, and this would be a bad path. All this might seem a bit confusing when I'm just talking about it on a higher level, so let's go through an example. So let's look at this example where the target is 3, and the numbers in the list are 1, 2, and 4. The first recursive call would be 1 from the num list. We subtract off 1, making a new target of 2. Remember, our base case is if the target is exactly 0 or if it's negative. Here, the target is 2, which is still positive, so we make another recursive call with the first number in the list, which is again 1. We also subtract off this number for a new target of 1, and since 1 is still greater than 0, we're going to do this again, and subtracting off 1 from 1 makes our new target 0. Now notice that this target is a base case because it's 0, and it signifies a valid combination, so let's add 1 to our overall counter. Note that these stack calls would be as if we started with the original target of 3, subtracted off 1, then 1 again to land exactly at 0. Thus 1 plus 1 plus 1 would add up to our target of 3, so it's a valid combination. Now let's move back up our recursive tree. In this recursive call, we were on the first number in the num list, which was 1, so now let's move on to the second number of 2. After we subtract off 2 from the target of 1, we get a new target of negative 1. A negative number signifies a base case where we would have overshot our target. In this case, it would be as if we started with our original target of 3, subtracted off 1, then 2, causing us to overshoot the 0 for negative 1. So we do not add to the counter and move back up the recursive tree. So we just tried the 2 and that wasn't successful, so let's try the 4. Subtracting off 4 would cause us to have negative 3 as our new target. And again, a negative number represents the base case in which we have overshot our original target. In this case, it would be as if we started with our original target of 3, subtracted off 1, then 4, which caused us to overshoot the 0 for the negative 3. Since we overshot, we do not add to our counter and move back up the recursive tree. Since 4 was the last number in our num list, we're done with this recursive call and move back up the recursive tree. Here we are on the first number of 1, so we are now going to try the next number of 2. This results in the new target being 0. When the target is 0, it represents a base case where we have successfully hit our original target. So we are going to add 1 to the counter, making it 2. Notice that this represents the combination of 1 plus 2 equaling 3. Since this is the base case, we're going to move back up the recursive tree. And in our previous call, we just tried the 2. So we're now going to try the last number in num list, which is the 4. Doing so causes our new target to be negative 2. This is a negative number, meaning we overshot our original target. In this particular case, it would be as if we started with our original target of 3, subtracted off 1, then 4, overshooting the 0 for a -2. Or another way you can think of it is the combination of 1 plus 4, which is 5, which overshoots our target of 3. Because we're unsuccessful, let's move back up the recursive tree. Now in this stack call, we just finished our last number in the num list, so we're going to move back up the recursive tree. In that stack call, we were just on our first number, so let's try the second number, which is the 2, in the num list. This has us subtract off 2, leaving us with a new target of 1. This is not 0 or a negative number, so let's keep making recursive calls, starting with the first number in the list, the 1. This leaves us with a new target of 0, which is a base case of a valid combination. This would be as if we started with the target of 3, then subtracted 2, then subtracted 1 to get 0. This represents the 2 plus 1 combination, which is obviously a valid combination summing to 3. So let's add 1 to our counter. Since this was a base case, we're going to move up our recursive tree. Now we're going to try the next number in num list, which is 2. This causes the new target to be negative, which is the base case where we overshot. So let's move back up the recursive tree. For this stack call, let's try the last number in the list, which is 4. This results in the new target being -3, which is also negative, so let's move back up our recursive tree. Now since we are finished trying the last number in the list, let's move back up the recursive tree again. For this stack call, we were on the 2, so now we just have the last number in the list, which is a 4, to try. Trying the 4 results in a new target of -1, which means we overshot, and we move back up the recursive tree. Now since we have tried the last number in the list with the original stack call, we are finished with the entire thing and return a 3, which is the correct answer. Okay, so now that we have traced through the overall algorithm, let's look at the actual code. So we will start off with the base cases. The first is that, as we mentioned earlier, if the target is 0, it means we're able to subtract the numbers perfectly, so we're going to return a 1. This is effectively adding 1 to our overall count. The other base case would be a new target being negative, meaning we overshot when we were subtracting the numbers. Here we return 0, effectively adding nothing to our count. Finally, we have the for loop and the recursive calls. This part of the code runs a for loop for every number in the num list, and for each of those numbers, we're going to make a recursive call to the function. However, we subtract off x, and the result is going to be the new target in the recursive call. We then add the result to a count variable, ultimately returning that count variable. I'm not actually too sure about the time complexity for the solution, but I believe it is roughly O of a raised to the end, where n is the target and a is the number of elements in nums. This is because for a recursive call, it can branch out into a more recursive calls because each recursive call makes a branch for each element in nums. For space though, it is O of n because worst case is that the number 1 is one of the numbers in the num list, and we would subtract off 1 from the target one by one. This would result in n simultaneous recursive calls, so our space complexity would be O of n. Okay, so that concludes the brute force solution. It's a good solution, but it's exponential and too slow. So at this point, I would recommend you pause the video and try to come up with a faster solution. Assuming that you've given it a try, let's look at the first way we can improve upon our brute force solution. The first way is that we're going to employ the memoization technique that is common when trying to speed up recursive solutions. Memoization is where we store all the subproblems we solve, so that if we come across an overlapping subproblem, we don't need to waste time to compute the solution again. I'm going to assume that you're somewhat familiar with this technique, but if you're not, you should still be able to follow along. Let's go back to our previous example to see where an overlapping subproblem could occur. If we look at the history of the recursive tree in our last example, we can see that there are 2 recursive calls where the target is 1. This means for the second recursive call, we're wasting time solving a subproblem which has already been solved in the past. So the way we can avoid this is storing the result of any subproblem we solved in an array. That way, if we encounter the same subproblem, we can just access the array in constant time and get our answer. So let's take a look at the code. On the left side, we have our old brute force recursive approach, And on the right, I'm going to show the changes we need to make. So our first change is that we're going to make a helper method. We are also going to create an array called memo. This is going to be of size target plus 1 and will be passed to the helper method. Each index in this memo represents the answer to that particular target. So for example, the second index is going to hold the count for the target equals 2 subproblem. But for now, they're all going to start off as -1, and I'll explain why in a moment. But before I do, we're going to keep our two base cases the same, and we're also going to have a similar for loop. The only difference now is that we're going to recursively call the helper method, and we're also going to pass along the memo whenever we call this method. Another change is that we have to store our count in the memo before we return it at the end of the function. This way, we can access the value if we encounter the same subproblem. And finally, we need to check if we have already solved the problem. How will we know if a subproblem has already been solved though? Well, remember we initialized the memo to be all -1s, and this is why we did so. Because if we had already solved the subproblem, then we should have updated that slot in the memo, and since a count has to be 0 or more, it can't be negative. This means that if we check the memo and the value is greater than a -1, we have solved this subtarget in the past, and we can now just use the array and return the stored answer in constant time. So these are all the changes that we need to make, and let's see how this improves our time complexity. The time complexity is improved to O of n times a. This is because in worst case, there can be n subproblems we need to solve with recursion. After that, the values will be cached in the array for constant time access. Each of the subproblems takes a amount time because we need to loop through the num list, so since there are max of n computations, each of which will take a time, the worst case time complexity is O of n times a. For space, we're going to be using n, or n plus 1 actually, extra space for the memo, but we can ignore the +1 and just say that the space used grows linearly with the target. Okay, so now that we have discussed this top-down approach with memoization, let's take a look at the second way we can speed up from the brute force solution, which is the bottom-up approach. For this solution, I think it's a good idea to show the code right away and trace through an example as I explain why it works. So if at the beginning you're a bit lost, don't worry, just keep watching and hopefully by the end of the video, things will become clear. So here's the code. If you're already familiar with dynamic programming, it might be worth the effort to pause the video here and try to explain to yourself what's going on. But if you've already tried, let's go through the code with this example where nums is 1, 2, and 4, and the target is 5. So the first line of code creates an array of size target plus 1. Before we move on to the next line, let me try and explain what this array is going to represent and why we need an extra slot. So with all DP tables, I like to think of each slot as a question. And the questions for the slots here is how many ways can I use the nums list to form the number at that index. So the third index would be how many ways can I use 1, 2, and 4 to sum to 3. The fourth index is how many ways can I use 1, 2, and 4 to sum to 4. And the final slot is the answer to our main question. How many ways can I use the numbers 1, 2, and 4 to sum to the target of 5? Note that since arrays start indexing from 0, this is why we need the array to be 1 larger than the target. It should make sense then that we're going to ultimately return the last value in the array because that value represents the number of ways we can use nums to sum to our target. And this is the overall question. For now though, everything is going to start off at 0, and let's go back to the beginning of our code. Back at the beginning, we're going to manually set the 0th position to 1. This is because this slot represents the answer to the question, how many ways can we sum to 0 with these numbers? The answer is 1 because we can choose nothing, and this is the only way to sum to 0. It is the empty set in a sense, and we need to manually set this to 1 to kickstart the algorithm. Next are the for loops. The outer for loop starts with I on 1, and then we see an inner for loop that says for x in nums, if I minus x is greater than or equal to 0, then add to dp of I minus x. This means for every position I, which represents a subtarget, we're going to check and see if the subtarget minus every element in num list is greater than or equal to 0. If it is, it means that we should add the number of combinations for the subtracted number to this subproblem. This might be a bit confusing, but let's continue tracing and hopefully things will clear up. So first, I starts off as 1, and x also starts off as 1 because x is the first number in the nums array. So I minus x is 0. This means we enter the if clause and add dp of I minus x, which is 1, to dp of I, which is currently 0. Notice that this represents the number of combinations to form 0, which is the empty set, plus 1, which correctly equals 1. Now we move to x being 2. This means that I minus x is negative 1, which is not greater than or equal to 0, so we move on to the next number. This represents the fact that if we have the subtarget of 1 and we subtract 2, then we have overshot into the negatives, which means you can't find a combination. Moving on to x equals 4, again, this causes us to overshoot to a negative number, so we move on. And since we're done now with the inner for loop, let's move I to 2 for the next iteration of the outer for loop. Now I is 2 and x is 1. 2 minus 1 is greater than 0, so we enter the if clause. dp of 2 minus 1 is dp of 1, which equals 1, so we're going to add 1 to this I slot. Notice for this subtarget of 2, this represents the combination of 1 plus 1, which equals 2. Now let's move on to when x is 2. I minus x is 0, which is greater than or equal to 0, so we enter the if clause. dp of I minus x is 1, so we are going to add 1 to the I equals 2 slot. Notice again for this subtarget of 2, this represents the combination of 0 plus 2, which equals 2. Now we try the last number 4. I minus x is negative 2, so we do not enter the if clause and move on. This concludes the inner for loop, so let's move on to the I equals 3 iteration of the outer for loop. Now for I equals 3, let's start with the first number in the nums list. I minus x is 2, so now we add the I equals 2 slot to the current total. The reasoning behind this is that I equals 2 represents all the ways we can use the num list to form the subtarget 2. So now if we have a 1, then we can reason that if we add 1 to all the possible combinations summing to 2, then these combinations will now sum to 3. In this case, there are 2 possible combinations of summing to 2. We can say 1 plus 1 or just 2 itself. So now if we add 1 to these 2 combinations, those combinations now sum to 3. So we account for this by adding 2 to our I equals 3 slot. Now let's move on to the next number of x equals 2. For x equals 2, I minus x is 1. So we're going to enter the if clause and add the quantity in the I equals 1 slot into this I equals 3 slot. In this case, the quantity is 1. Again, the reasoning for this is that there is one possible way to use the nums to sum to the subtarget of 1. So for all possible combinations of summing to 1, if we add 2 to those combinations, we'll get a sum of 3. In this case, there's only 1, and this represents the combination of 1 plus 2, equaling our subtarget of 3. Now we move on to the final number, which is 4. Now I minus x is less than 0, and this once again means we overshot, so let's move on to the next iteration where I equals 4. For this first number, I minus x is 3. This is greater than 0, so we enter the if clause and add dp of 3 to dp of 4. Again, this represents us taking all possible combinations that can form the subtarget of 3, which in this case is 1 plus 1 plus 1, 2 plus 1, and 1 plus 2. If we add 1 to all these combinations, then we'll be able to sum to 4. Therefore, we add these to dp of 4. So let's move on to x equals 2. Here I minus x is 2, so we enter the if clause and add dp of 2 to dp of 4. This represents us taking the possible combinations that sum to 2. In this case, there's 1 plus 1 and 2 by itself, and if we add 2 to these combinations, we get our subtarget of 4. This is why we're going to need to update the I equals 4 slot by adding 2 to it. Let's move to our final number of 4. Here I minus x is 0, so we enter the if clause and add dp of 0 to dp of 4. This represents us using just 4 itself to sum to 4. The 4 is the last number in the nums list, so let's move on to the next iteration of the outer for loop, where I equals 5. Starting with the first number 1, we see that I minus x is 4, so we're going to add dp of 4 to dp of 5. Again, the logic behind this is that we're taking all 6 ways we can use the nums to form the subtarget of 4, which I've listed here. Then we add x, which is 1, to all of them, and this makes all those combinations equal to the target of 5. We account for this by adding all those 6 combinations to the I equals 5 slot. Let's move on to the next number now. So now x equals 2, which means I minus x is 3, and since x is greater than 0, we're going to add dp of 3 to dp of 5. Again, this is us taking all the combinations which add to the subtarget of 3. There are 3 combinations, which are 1 plus 1 plus 1, 1 plus 2, and 2 plus 1. We can then add 2 to all these combinations to form 5. Therefore, we update our I equals 5 slot from 6 to 9. Finally, we go to the last number of 4. I minus 4 is 1, so we're going to add dp of 1 to dp of 5. This represents us taking the number of ways we can form the subtarget 1, which is just 1 itself, adding 4 to it to form 5. Adding 1 changes our final total to 10, and now we are finished with this portion of the algorithm and exit both for loops. At this point, we return dp of target, which is our correct answer of 10. Before we move on though, I want to point out something. Remember that at the beginning of this problem, I said that each slot represents the answer to the question, how many ways can I use numList to form this index's number? And notice how for not just the last slot, but for all the slots before it, we have the right answer. There's one way to sum to 0, one way to sum to 1, 2 ways to sum to 2, 3 ways to sum to 3, 6 ways to sum to 4, and our final answer is that there are 10 ways to sum to 5. I think it's very helpful to think of most dynamic programming problems in this way. Rather than just thinking about the code and the DP table, try to ask yourself, what does each slot in this DP table represent? Or what question does it answer? I think if you understand the meaning behind the slots in every dynamic programming problem, when you encounter other dynamic programming problems, it will become much easier for you to come up with a solution. Anyway, let's move on to the time and space complexity for this algorithm. So the time complexity for this algorithm is pretty straightforward. We run the outer for loop from 1 to the target, which is n times, and for each of those iterations, we have an inner for loop which runs the number of elements in the nums. This means the algorithm is O of n times a. For space, we have our dp table, which grows linearly with the target, and this is O of n. So those are the 3 main solutions to this problem. There is the brute force recursive approach, which can be improved when you implement memoization, which is known as the top-down approach. And finally, there's this approach here, which is known as the bottom-up approach. With that, I hope this video helped you better understand this combination sum problem. As always, if you found a mistake or have any extra questions, please feel free to leave them in the comments, and I'll do my best to get to them. But regardless, thank you for watching, and I'll see you in the next video.